Okay, so if you remember, last time we defined Poisson Lie groups. So what was it? So it is just a Lie group with a Poisson structure, with pi or whatever you can call it, a bracket, is always such that the multiplication is Poisson. We didn't see too many examples yet. There were like examples that we really saw were when, say, pi is equal to 0. That's a great example. It satisfies it. Or you can take arbitrary g in this case. Or we can take the dual of a Lie algebra with its standard Poisson structure, which is a commutative group. So with plus. That's an example. And there is another example if you looked at the exercises. There is another example, which is this affine group, like transformations of the form x plus b, where a and b are real numbers. And you're supposed to check that when we take this Poisson bracket, then it's a Poisson Lie group. And it is. So today we'll see, in principle, many examples. But before that, there is something that is left to be proven. Because last time we proved that at least one connected Poisson Lie group G is the same thing as a Lie bialgebra. Structure G, which I will remind you it means that it's a Lie algebra. That's the Lie algebra of G. So there is a Lie bracket. And there is also a Lie cobracket, or a Lie bracket on this dual, which satisfies some condition which, well, I'll remind later. For the moment, we don't need it. But there is one thing that remains to be seen. It is in the proof, and the statement was, okay, proposition that if A and B in T poly G are multiplicative, then their bracket is as well. So multiplicative means there are several ways how to put it, but one way how to put what multiplicative means, that we have this map from G times G to G at M. And now A is multiplicative, means that if you put A on the first copy of G, another A on the second copy of G, and we push it forward, we get A back there. So let me write it like this way, that M star of A1 plus A2 is equal to A. That's just notation for putting it either on first G or on second G. So let's try to prove this. It's sort of a very, very simple thing. But when I try to prepare the proof, I overcomplicated it. So let's see. So we need two things. The first thing is that, say, if M and N are manifolds, then we have, when we take T poly of M or T poly of N, these things are naturally included in in polyvector fields on M times N. And the first statement is that this is actually a map of a morphism of graded Lie algebras. Well, I should shift degrees by 1 to make it morphism of graded Lie algebras. But it means just that when you take two things from here and see them as polyvector fields there, and their bracket here is the same as was the bracket there. The same thing here. And finally, this direct sum means that when you take somebody from here and somebody from there, then their bracket here is 0. That's the statement. Is the statement sort of clear? This is one thing that we need. And the second thing that we need is that if it's some sort of functoriality of Schouten bracket, that if you have a map from M to N, and for us it's enough to suppose there is a submersion, is a, okay. Of graded Lie algebras, that's one thing. And if we have a submersion, then a Schouten bracket is, say, functorial with respect to the submersion, which more precisely it means. And if what we need, like A and B in T poly M such that M star of A and M star of B are well defined. We have two polyvector fields which are projectable. Then, when we take their Schouten bracket, it's still projectable as the Schouten bracket of the projection. So we should check these two things, so let's do it. Maybe let me put it, both things should be sort of obvious when you look at it, what it actually means. But let me say, restate this first property as a slightly stronger statement, which will then imply also the second property. The thing is that when we have these T polyvector fields on M times N, and this algebra contains naturally the tensor product of the algebra of polyvector fields of M and of polyvector fields of N. Or if we were like in algebraic geometry, this would be just equal to the tensor product. Here we're in differential geometry, so we can just say that it's dense or something of this sort. Whatever. And in fact, it's dense. What a statement really is, okay, that's statement, say, for vector spaces. It's also statement for graded commutative algebras that I guess you see directly. But it's also statement for Gerstenhaber algebras, where the bracket here is defined so that things from here commute with things from there. So it's a Now, one way how to see it, I can leave it, say, a little bit up to you. One way how to see it very easily is to look at it, say, in coordinates. That's a very bad thing to do, but it's also very efficient. You look at polyvector fields written in coordinates. Now you look at how did this Schouten bracket, well, the formula for a Schouten bracket, and you see that like coordinates on M just don't talk to anything corresponding in N. therefore we have this morphism. But maybe a better way, more invariant way how to see it is to say that the Schouten bracket is uniquely defined by the fact that the bracket of a vector field with a function is equal to x being applied on a function, and the bracket of two vector fields is the bracket of two vector fields. And now you see, you take, say, a vector field from here and a function from there. Well, this guy is 0, yeah, so they commute. Or you take a vector field from here or a vector field from there. It gives you a vector field on m times n, but they certainly commute. So it's just the statement that these two expressions on m or on n go to the same expressions on m times n, and when you take something which is mixed, then you get 0. It's only this. Okay, so then one just follows from the fact that how do we get this thing? Well, we just take t poly tensor with 1 plus 1 tensor with t poly. We only take things of the form m plus t poly of n is simply contained in t poly of m tensor with t poly of n, where we send a plus b to a tensor 1 plus 1 tensor b. So the fact that this preserves the bracket is just the statement that this preserves the bracket. And the second thing, now the second thing is, as I said, is again best seen in coordinates. I will do it somehow semi in coordinates to make it more proper, maybe. You see, locally, we can certainly imagine that M is really projection from R n plus whatever k to Rn. And let's have a look at those polyvector fields here which are projectable. Now, what does it mean when the polyvector field there is projectable? It's going to mean just that it doesn't depend on these coordinates. It has some coefficients which are functions on of n plus k variables. Being projectable means that it doesn't depend on those k additional variables. So, say projectable T poly of R n plus k. I can write it this way, that these are T poly on Rn. But that's not all, because well, it shouldn't depend on those coordinates, but we can have there all those vectors, those coordinate vectors or coordinate polyvectors, including those coordinates. So it's tensor with wedge of Rk. So say it looks something like this, that if the coordinates here are some, I don't know, xi's and ya's, coordinates there, so these are I is equal to 1 up to n, and sorry, a is equal to 1 up to k, then the thing in here is going typically to look as a combination of f, which is a function of x's, and then you can have n up to, I don't know, L something, but there might be also some d over dy's there. I don't know, M. So this is a typical projectable polyvector field over there. But what now happens when you take the bracket here? Or, you know, we take two things from here. Say, what is their product? Their ordinary product is going to be just the product here and the product there. And why is it so? You see, what is happening that this guy should be seen as, and it is really part of T poly of Rn tensor with T poly of Rk. So what's happening here? That here we just take constant polyvector fields. That's the difference, right? This is including there, where we take, so here we take, this contains weights of Rk, which are constant. And we know exactly what the Schouten bracket here is. It's just the bracket there plus the bracket there. But when you pass to those constant polyvector fields, there is no Schouten bracket anymore. Or two constant polyvector fields have bracket 0. So the bracket on T poly Rn tensor wedge of Rk is just bracket. It's simply this on T poly, sorry, Rn. So we're taking the bracket only here. Things here just get multiplied. There is nobody's ever differentiating anybody there. And now I can just say that what we saw anyway from the very beginning, that this implies that when we take M star of AB, we get the bracket of M star A with the bracket of, with the M star of B. Say since what is doing M star? M star is, well, not touching this guy, and it's removing everybody from here except for one. So M star is the augmentation for, or how it's called. M star maps. Which is going this, from there is the projection to wedge 0 Rk. Okay, great. So that's the end of this sub-proof. Just of the statement that when we have a product, then these things are going to nicely commute, and that we have this functoriality. One thing which was not nice about those proofs were that it was written in coordinates. But so I gave you an exercise, you don't know yet, about proving this second statement for arbitrary M, for something which is not a submersion. Well, one cannot do this dirty trick, but one needs to do something more conceptual, but it's now up to you to do it. Okay, so now when we have this, I can finally prove So to prove this, well, compatibility of this with multiplicative T-poly of G. So once again, what does it mean that A is multiplicative? It was that when we put A on first G and on second G, and we take M star of that, we get back A. M star of A1 plus A2 is equal to A. We have this M. Okay. So let's now try to compute something like, when we take this with A and B, that's going to be M star of A1 plus A2, M star B1 plus B2. So for the moment, I just use that it's multiplicative. Then we can use this functoriality under submersions. So it's going to be M star of A1 plus A2, B1 plus B2. And you see now we have some polyvector field on first G, polyvector field on second G. Here, again, on first G, on second G. And so this first statement was that they simply don't communicate with each other, this first and second copy. And we're only going to take the bracket here and the bracket there. So it's M star of what? Of A and B put on the first copy. So that's the bracket between this and that. And then we have this second thing. AB. And that's what we wanted to prove. No? We wanted to show that this bracket of A with B is multiplicative, which just happened. Was there some miracle that? Yes. Yeah, there's maybe some circular reasoning. I hope there is none. But
the mixed terms,
why this is equal? Why this is equal to that? Yeah. That was this one of those statements that when we include into polyvector fields on the product, polyvector fields on the first factor, and the polyvector fields on second factor, then what's happening that things from those two factors that are going to commute, and when we take things from the same factor, then their bracket is going to be just the original bracket on it. So that's exactly what's happening here, right? That we separate, there are those mixed terms which vanish, and those non-mixed terms, I can somehow move this one outside. Okay. Okay, so that was a proof. As usual, when there is a proof, you can forget it until exam comes, maybe. But let us now look at something more interesting. Now, let me now recall what is a Lie algebra. So what was it? You see, it was a Lie algebra, that it was G with a bracket. There was a Lie cobracket, delta. So that's something which goes from G to wedge to G, which when we take the transpose of that, so this guy is a Lie bracket. Okay, so there was a Lie bracket, Lie cobracket, but there was also some compatibility condition, which we somehow computed. Now I just write it down. this was the delta of the bracket of two things, is equal to add x applied to delta y minus add y applied to delta x. And now our aim is to understand better this relation, or rather to re-express it in some more normal terms so that we can find some examples, because for the moment we don't have many examples. So let me start just with some drawings, so some diagrams. So the Lie bracket is going to be reasonably represented as that there are two inputs and one output. Okay. The co-bracket has one input and a sort of two outputs. I mean, it goes to from G to G tensor G. But to interpret it the other way, that when we enter two things from G star, it's going to be again a Lie bracket. And what is now this relation, this co-cycle relation? I should try to draw what that gives. So what is star? You know, to make it somewhat, those diagrams somewhat nicer, I will also choose some A and B from G star, and now I will pair that star, or either right-hand side or the left-hand side, which has values in wedge to G with these two things, A tensor B. Just to get a number. So let's start on the left-hand side. So what's happening there? We take x and y. Now we enter into the bracket. It goes out. Then there is this co-bracket, and then we put here A and B, and that's it. Now the second thing, just add x on delta y. So let's see. There is this y. We apply delta to it. And now we're supposed to have this add of x. But you see, there is maybe one thing which I didn't quite explain, but I hoped you would understand, is that this guy is an element from wedge to G. So add means like that we're acting on the first copy, and plus we're acting on the second copy. Just the representation given like that. So it means we now have to take the bracket, which is adjoint action, but either here or there. So there would be two terms. There's x here. Okay, it just continues like that. There's A and B. And the same thing when it enters here, which I will draw in this way. Y. So what happened? Why is there a minus sign all of a sudden? You see, what I should have drawn is something like, I'll just erase this x. I should have drawn something like x entering from this side. But I prefer to have it somehow have a nice picture, so I put the x to the other side, but I just use Q symmetry of the Lie bracket. So that's why there is this minus.
Wait. Yep. So on the second one, I think you have x and y switch. Co-bracket x first.
Okay, well, you see, what I should really say, it's like add, let me write it like add 2. It's like that it's how we make G act on G tensor G. That we're acting on the first copy, and plus we're acting on the second copy. And it's the same put. And that minus sign is just because I prefer to have X outside so that we don't have a crossing here. So there is this skew symmetry of the Lie bracket which is happening here. That's why we have this minus. Okay, and now there is minus, which will be the same diagrams with what X and Y exchanged. Okay, so there is going Y, X. And plus XY. So is it clear? Just there's nothing really happening here. Let me just redraw this a little bit. So it's going to be, it's the same picture, but I'll redraw it anyway. X and Y. AB. Is equal to, and I'll just make this this middle line horizontal. So there's going to be X, Y, entering like this. AB, there's not another picture where we have also X, Y, and B, this guy. So it's plus. It's kind of the same picture, it's only this middle line is going the other way. And minus. Well, just the same thing, but with the X and Y exchanged, right? Y, X, A, B. Okay, that's it. No, for the moment, it might not be totally clear whether it helped us, but which is okay. But just for some spoilers, so what we're going to do, we're really going to combine those two diagrams and these two diagrams. So somehow this middle edge going either this way or that way is just going to become one edge without any arrow. Okay, that's what was the spoiler. I don't know whether it spoiled anything. But one thing that certainly we can see either from here or just looking at this, that there is now a perfect symmetry between G and G star in some sense. So one somehow consequence just of looking at the formula more closely. Is this thing that if G with a bracket and co-bracket easily by algebra, then when we take the dual, then G star, there is a natural Lie bracket on it, which is just given by delta. So with the transpose of delta. There is also natural Lie co-bracket because we have a bracket on G. So we take the transpose of the bracket on G, get a co-bracket on G star is also. Yes. Just, you know, what is a Lie algebra? That this is a Lie bracket, this is a Lie co-bracket, and plus that relation. That relation is clearly symmetric when you put it upside down. So it means that, in particular, if you have a Poisson-Lie group with Lie algebra G, then we know that G star is again a Lie algebra. And there is going to be a Poisson-Lie group with that Lie algebra, because it's again a Lie bialgebra. So Poisson-Lie groups somehow come in pairs. Did we already see an example for this? Yes. In fact, we saw two of them. We didn't see too many examples of Poisson-Lie groups. There were like the trivial Poisson-Lie group or the dual of a Lie algebra. Dual of a Lie algebra with plus as an operation. And this is exactly an example of a pair like that. See that you take. So when you take G with a bracket and with delta equal to 0, and what is the corresponding dual Lie bialgebra? It's going to be just G star with 0 bracket. And with the transpose of that guy. So the corresponding group is G with Poisson structure equal to 0. The corresponding group for 0 bracket, that's not going to be much. It's just going to be G star as vector space or as a group. And from here, it's probably not very difficult to see, or certainly one can easily check that when we take this, when we take the standard, or what is called Kirillov, Kostan, Suryo, or Lie, Poisson, or whatever are all those names attached to this super simple linear Poisson bracket, which is on a dual of a Lie algebra, then its linearization at the origin is exactly the Lie bracket. That's how it was actually defined. We don't have to linearize it; it's already linear. Right? So we get that thing. So here you see an easy pair of two Poisson-Lie groups that are dual to each other. And I promised you that we actually saw two pairs, which doesn't fit very much with what we saw. But there was just one more example. It was this AX plus B group. And it's a Lie bialgebra that, well, you were supposed to or are going to compute during the exercises. And the dual of that one is itself. So that's why it's another example. So we don't need a fourth Lie bialgebra because that one is self-dual. OK, so let's now start going to understand this thing. And the idea is that just Lie bialgebras are the same things as what is called Manning triples. So now the problem is to define what is a Manning triple. So a Manning triple, well, it's a triple. So that's, at least that part is good, right? So there are three things. The first thing is okay. First of all, a triple of things where there is going to be some D and G, and let me call this third thing as G prime. And now, the main difficulty in this subject is how to write a fracture D. I have no idea how to do it, so I always, when I do it, there is some kind of partial derivative or boundary, but it's supposed to be like this mat frac. D. That's probably a bit long to write, so this is just going to be my shortcut for writing that. Okay, where? So before the break, let me just finish the definition. First of all, this D is a Lie algebra with invariant inner product. Note it like this. What I should rewrite is symmetric, invariant, non-degenerate bilinear pairing, but I will just write invariant inner product. But what the difference is that this guy is not going to be positive definite. Actually, it's going to have a split signature, so it's going to have equally many pluses as minuses, as will follow from the rest. So that's one thing that enters here. So it's a Lie algebra with this invariant inner product. And G and G prime, part of D, are Lagrangian Lie subalgebras. What does Lagrangian mean in this context? Is Lagrangian with respect to this inner product means that when we take the would-be orthogonal complement, though it's not really complement, of G, the thing which sits inside of D, this should be equal to G. And the same for G prime. So that's what this Lagrangian means. And one thing that implies is the dimension of G is 1/2 of dimension of D. So there are Lagrangian Lie subalgebras, and finally there is some condition on those two subalgebras such that G intersection with G prime is 0, which then, given all those conditions, implies that D splits as a direct sum of G and G prime as a vector space. Okay, so it's this thing, this kind of triple, which is equivalent to a Lie algebra, as we'll see after a break. And it's very easy to find examples of these triples, which we'll also do after the break. Okay, so let me repeat that Florian revealed to me that I made a really idiotic mistake. And that was when I was talking about those projectable polyvector fields on whatever R n plus k. So just to straight it up. So we have, when you have a polyvector field on this guy, it's going to look like there are some of those dx's, several of them, and some d over dy's with various indices here. And for an arbitrary polyvector field, there will be a function of x and y. Now, when is it projectable? You see, when we make this push forward, what's happening? It kills all, whenever we see d over dy, it becomes 0. So all those which contain at least one of those d over dy's, they are projectable. They just go to 0. It's OK. It's only those that contain only exclusively dx's. But when we somehow push forward this guy to Rn, so here are coordinates x's and y's, here are coordinates just x's. So when we push forward this guy, which just remains the same thing exactly. So to make it projectable, it means that this coefficient shouldn't depend on y. So the condition is that when there is one of those d over dy's, it can be whatever it is. It's just when there is none of those d over dy's, then it shouldn't depend on x. But nonetheless, it is still true that when we take polyvector fields of this form, or here they are arbitrary, here they are somehow restricted, and when we take their Schouten bracket, then when it comes to this term, then the Schouten bracket is just happening here. There might be all kinds of things happening with those things, but when we project them down, they're going to disappear. So that's why it's still true that making first Schouten bracket here and then projecting is the same as first projecting and then taking the Schouten bracket. But anyway, in this next exercise set, you're going to have a very nice and geometric and whatever invariant proof of that stuff for arbitrary map, not for submersions, not for maps of this form. So I can say that at least partially the case is saved. Okay, so that far for this stupid mistake. And let's back to, but as I said anyway, it was just a proof, so who cares? Let's go back to these Manin triples. So some things that we can observe, given a Manin triple. So one thing we can observe that G prime can be identified with the dual of G via the pairing, right? So somehow we have this D thingy, and there is G and G prime sitting inside, and the pairing between this and that is going to be non-degenerate necessarily, because those things are, so it's enough to say that this guy is Lagrangian. Therefore, like pairing with anybody who is like transverse to it is going to be necessarily non-degenerate if the pairing itself is non-degenerate. Okay, so we can identify it that way. So from now on, I will use actually G star for the G prime. That's one thing. Another thing, one can say, what actually is that pairing now? You see, the pairing just on G itself is 0, because that thing is Lagrangian. It's self-orthogonal. The pairing restricted to G star is also 0. The only non-zero pairing is between G and G star. Even one more reason why the pairing must be non-degenerate. So it means that this guy on this D, which is G plus G star, is simply the pairing between G and G star. And I will write the theorem soon, but still I must just to say to more or less prove the theorem before I write it, to understand what's going on. You see, we have a Lie bracket on D. So therefore, we have a Lie bracket on G and on G star, which are Lie subalgebras. That starts looking good, right? So we have a Lie bracket on G and a Lie bracket on G star. This might look like a Lie bialgebra, provided there is this condition satisfied. Mm-hmm. So we have Lie bracket on G and on G star, but to have a Manin triple, we should actually have a Lie bracket on G plus G star. So in principle, there might be more information inside. But in reality, we don't have more information. Why? Now, if we take, say, X in G and A in G star, can we compute the bracket between X and A just using the bracket on G and the bracket on G star? Yes, we can. Why? Because when we take the pairing with some B, which is also here, we just use invariance of the inner product, right? So we get that is equal to X AB. And similarly, if we take like Y XA, sorry. So therefore, one can say that the Lie bracket on, well, first of all, the pairing on D is just specified. It's just given this way. It's simply the pairing between G and G star. And the Lie bracket on D, the entire Lie bracket on D, is given by the Lie bracket on G and the Lie bracket on G star. You see how to compute? Well, this gives us the part of the bracket between X and A that lives where? We're pairing it with things in G star. Yeah, exactly. So this gives us the part which lives in G. This gives us the part which lives in G star. So one can even write something like that. XA is the part that lives in G. Okay, well, it's like, I guess it's, okay, I'll write it this way. It's add star X on A minus add star A on X. So this guy lives in G star. This guy lives in G. If you just look at those formulas, that's exactly what's happening. See, this is what's supposed to give us this the G part, that there is that minus sign coming from the just definition of add star of the coadjuvant action, and the same appearing here. It's not that we're not going to like, need this formula. It's just one can deduce it if necessary, right? So just to sum it up, what we found that D with its product, with its inner product, and with the bracket is given uniquely by the Lie brackets on G and on G star. Okay, here we have some more formulas if necessary. These are formulas for those mixed terms, which we can write this way, which is somewhat less useful. This is sort of more useful in this context. But the final question is, okay, let us define the Lie bracket on D using these formulas. That means that the Lie bracket on G is the Lie bracket on G star is the one which is on G star, but the mixed bracket is given by these formulas. And the question is it actually a Lie bracket on D? Does it satisfy Jacobi identity? That's a non-trivial question, right? Or non-trivial, I mean, it's easy to answer, but it needs to be answered. And the answer is, it is a Lie bracket if and only if this. So let me now finish it. Theorem, which was before this title, just says that, whatever, I'll write it now this opposite way, that Manin triples are the same things as real bialgebras. And for the proof, as I said, that gives, okay, how is it? That given, say, Lie brackets on G and G star, there is a unique candidate for the Lie bracket on D. And we only need to verify whether this Lie bracket satisfies the Jacobi identity. So what is the Jacobi identity? Jacobi identity is like U, V, W plus cyclic permutations is equal to 0. Now, in this context, when you have a Lie algebra with an invariant pairing, or we would like to have a Lie algebra with an invariant pairing, it's good to pair it with somebody else. So I will pair it with the natural letter is something like triple U, probably, in this context. So the question is whether this is equal to 0. The thing can be, okay, that's just a matter of style, how to write it. So I can write it this way. It's like UV, and then I may push this W to be paired with this triple U. And plus cyclic permutations in UVW. Okay, so we need to verify, we need to understand when this guy is equal to 0, either written this way or that way, it doesn't really matter. And now the statement is that or, how would I draw it? How would I draw this? Either U, V, okay, or maybe I can put it this way, or equally well, this U, V, W, triple U. So what kind of diagram one can draw? So there are these U and V coming in. And I will stop drawing arrows because here we have this invariant inner product. So it doesn't really matter whether the thing is from D or from D star. It doesn't matter which way any arrow goes. So let me do something like this. Then what do one do? One would then take the bracket with W, and finally pair the outcome with this triple U thing. Or is written the same way, just to see that what's happening here, that we can just move these around. It is the same thing, that you take the bracket of U and V, there is this outcome. Now, from this side, we take the bracket of W and, sorry, this is, yeah. I designed this wonderful letter and now I cannot. So we take the bracket of these two, the outcome, and now we take the pairing. Oh, it's the same diagram, so it's like this guy. And we need to take Now secret permutations between between these 2, 3 letters, and the question is whether the sum is equal to 0. So this plus this O V W U. So we're asking this kind of thing. And we need to verify it for all U, V, W, triple U in our D, which is just G plus G star. Or in other words, it's enough to take these things from G or G star and take all possible combinations. There are many of them, but we'll see shortly that most of them are sort of trivial, so there is only one combination that really needs to be verified. So let us take these things. Now, using this decomposition, I can write that okay. Let me think about. Okay, so let me write here that it's enough that we can now suppose that, say, U is equal to X, V is equal to W, those things are in G, and sorry, W is equal to Y, sorry, and W equal to A, triple U equal to B in G star. The reason for doing that is that for any, how to put it, that when all 4 of them are from G, then the outcome is simply 0. There is just taking inner product and staying within G is always going to give us 0. So there's some sort of empty thing. When 3 of them are from G, and 1 of them is from G star, what's happening then? You see, for example, it doesn't matter which one, so let me just take this triple U thingy from G star and everybody else from G. What are we then verifying? We're just verifying the Jacobi identity within G. And so this is just somehow output. You can cover it. These things are from G. That's the Jacobi identity within G. We know that it's satisfied. We know that G is a Lie algebra. Okay, so let me write the possible cases. Say all leaves in G, that's going to get 0 automatically. Just because this inner product restricted to G is equal to 0. Now 3 in G and 1 in G star, that's going to get Jacobi for G. Now the same is for when we're here in G star and here with G star and G. So the only non-trivial case is when 2 are in G and 2 are in G star. So this is the only Jacobi identity that we need to verify. And what is it? That's what's written here. Exactly, this is like one term, another term, another term, And for these, you see these arrows going either this way or that way, where in D is a direct sum of G and G star. That's why we have this. That's why we have this sum happening here. So somehow this guy is equal to that guy plus that guy. For all those leaves, well, we only have arrows going one way because it doesn't make this, well, if you took the arrow going the other way, we would get 0. Whereas somehow here we're pairing with somebody in G star. We need to take the arrow that way. If you took it the other way, we would just get 0. But for this internal edge, there is no such thing. That's why we need to take the sum of those two things. And what is written here is simply a Jacobi identity. OK. No, you didn't understand anything by looking at your faces, or you're just too bored or something. So what should I ask you? Tell me what I should ask you.
Well, I have a sort of questions. So it seems to me, maybe I'm wrong, the Manning triple seems to be basically determined by this sub-Lie algebra G, because then the other one's got to be the dual and all that.
You need to know both the bracket and the co-bracket. Or you see, you need to know the bracket on G and the bracket on G star. So you can certainly say that you just have this Lie algebra G, but together with the co-bracket, which is the bracket on G star. Okay, so and this is simply this cocycle, the delta of xy. Let me call it the end of the proof. I have to say there are some much more conceptual ways how to prove this theorem. This was only like taking it and proving it as it was. But for our purposes, it's OK, because as I said, this is not really a course about Poisson geometry. So let's just leave it this way. Maybe one thing that might sort of help you, or does it really? I'm not sure. Because it might be also quite confusing in some sense. That if I draw this vertex, which really means u, v, w is supposed to be a number. The number is u, v, w, that thingy. So this kind of that kind of vertex in this Manning triple context, it's going to be composed of. You might have these things, but I should take a sum over all possibilities where are those two incoming arrows and one outgoing arrow, but I'll leave it just that way, and plus one might have. Okay, let me just draw it the opposite way. There is one incoming and two outgoing. But in principle, we see that this guy is like somebody from wedge 3 of D star or D as you wish, which then decomposes as G tensor wedge to G star, and plus there is G star tensor wedge to G. But there are two more components in principle. There is also wedge 3 of G and plus wedge 3 of G star. Now, the Lie bracket on G is this part of that guy. The Lie bracket on G star is that part of this guy. And these things, what are those things? 0. They are 0, yes, because what are they? Here we should take three things which are probably from G star, or say from G to take it here. So if U, V, and W are all from G, and what's happening? that bracket is somebody from G, and the bracket, and now the pairing of somebody from G with somebody from G is 0 because G is Lagrangian. So whenever I see a vertex, it's always there are either 2 incoming and 1 outgoing, or 1 incoming and 2 outgoings. But we can never have like 3 incoming things or 3 outgoing things. Okay. So let us now pretend that we understand that this is true. And let me tell you all those examples. But what we really only need from this theorem that whenever we find a Manin pair, sorry, a Manin triple, then we have a Lie bracket on G, a Lie bracket on G star, and that's a Lie by algebra. Like the rest was just somehow a way how to see that it's indeed true. But let's look at examples of Manin triples. One thing might be the following. Let's take, for D, I will take SL2, oh no, sorry, GL2. You see that D should be even dimensional, I guess. If it's G plus G star, then SL2 probably wouldn't work very well. Now, for that pairing thingy, on GL2 in principle, but it's like it's a one-dimensional thing plus SL2. So we have a nice pairing on SL2 and nice pairing on this R, or one-dimensional thing. We can just multiply them with random coefficients. And the particular random combination that works very well here is then when I take the determinant of U. That's a quadratic form for 2x2 matrices. And now for G, I might take this guy. From G star, I might take this guy. And so this is the one-dimensional affine, or the Lie algebra of affine transformation of a line. That's again the same thing, isomorphic thing. Did we see it? Yes, that's what corresponds to that. That corresponds to the AX plus B group Poisson. Okay, so that's an example that we already saw. Now, how about some examples that we didn't see? It's actually going to be a generalization of this one. And you tell me whether you know all the terminology and whether you know it much better than me, because, well. So I will start with G, which is going, okay, let me start. Let me call it G. That's going to be a semi-simple. And since, well, in this course, it's not important, but we're working over real numbers, so everything is like C infinity. So I'll take it semi-simple and split. Meaning that all the roots are real, everything is real somehow. Like, for example, SLN is going to work perfectly well. And now for D, I would take G direct sum with H. This is the Cartan subalgebra of G, say the diagonal matrices, if you wish. Here, I should also say what is the inner product. So for the inner product, there's a natural one, which is just Cartan. So sorry, killing, or whatever, Cartan killing. Killing thingy here. And I would take the killing thing here, but then it wouldn't quite work, so I will take like a minus killing. Just, it's a subalgebra here, so I'll take this killing thingy, but I need somehow to subtract it from there. So here I will take minus killing. And traditional and probably very bad way of denoting that it's minus is to put a bar over that, which in particular doesn't mean complex conjugation in this context, unless it does. But here, bar means just we're taking it with minus the expected inner product. Okay, so that's our D, but I should still say what is the Manin triple. The problem is that I use this G because it's somehow very natural to call it G, but our G's are not going to be that G because that's not half-dimensional inside. So let me now take B plus. Sitting in G is going to be a Borel. Tell me that, do you recognize the terminology? Okay, then everything is perfect. Like it would be upper triangular matrices, if you wish, in that case. But I need to put it in D, and the way I put it in D, now from that, I'll make this B plus part of G plus that H. How would one do it? You see, somehow, I'll put it somehow, write it diagonally. Diagonally means, what do I do? We have certainly a projection from B plus to H. And I take like this injection and that projection and take the diagonal map. But what it simply means that we take this upper triangular matrix and we assign to it, okay, that's part of all matrices, direct sum with diagonal matrices, and how? Well, here we just take the matrix itself and here we take its diagonal part. Just that thing. Okay, so this guy is a Lagrangian Lie subalgebra. And why is it so? Let's say check the dimension. Does it work? Yeah, what's happening here? You see, we doubled here this Cartan subalgebra. We added it there. So what's happening here? There is twice Cartan subalgebra, and there are all those root spaces. Now here is only once Cartan subalgebra, and there are only positive root spaces. So that's why the dimension of this is indeed half of the dimension there. And does it work with? Is it actually Lagrangian? Is it say isotropic with respect to this guy? How does it work? When you take two things from the corresponding to two things from root spaces corresponding to positive roots, then this Cartan killing form applied on that is going to be 0. It wouldn't work for things which are from Cartan, because certainly this killing form restricted to Cartan subalgebra is not 0. But that's why we're adding here this H and putting there this minus sign. That exactly is going to kill. That exactly is going to kill this killing form, which is the right thing to do. Let me maybe illustrate it on the case on when when G is equal to SLN. When you see it for SLN, then you see it for every other Lie algebra. And let us take some. Okay, X and Y are in this B plus. So there are going to be upper triangular matrices, whatever, something. Here there is 0. Now if we take if we took just carton killing in here, what would we get? It should be a trace of x times y. But when we compute the trace of x times y, the only thing that remains is this diagonal part, I guess, right? So it would be this x, or maybe x11 component times y11 plus x n times y n, just those diagonal. Just diagonal components. So you see everything that is somehow above that, everything which is in this nilpotent part that's going to vanish, but this thing doesn't vanish. So how do we solve this problem? We subtract the same thing. We don't want to see, so this would be just in G, but we want to compute it in D. We want to see it as a subalgebra in D, so that's where we see X as a pair of that guy and plus, so this guy, and plus just the diagonal part. Only the diagonal part. And then when we take this thing, well, we take this trace, which gives that guy, but minus the same stuff just for the diagonal part, which gives us 0. It's really very well designed, right? So it's just this. OK, so we have a one Lagrangian Lie subalgebra. We should get another one, which should be transverse to that guy. How do we get it? Well, there is a reason why I called it B+. So the other one is going to be called B-, exactly. I could also call it like C+, maybe. So another. So we take B minus in G, that's we'll say lower, or this is the opposite Borel, or lower triangular matrices. And now I need to put it into, I need to somehow map it into our D, who is G plus H with this bar thingy. But in such a way, I need to make sure that B plus intersection with B minus is equal to 0. Now, if I map it as before, that means that, well, just map it here and map it, project it there. It wouldn't work, right? There would be a big intersection. Just all diagonal matrices would be in the intersection. But there is an easy way how to get around it. You see, this quadratic thing is not going to change when I change the sign. So now the map is going to be, I map it here just by the inclusion, but I map it there with minus the projection. So this guy is inclusion and direct sum, or whatever, something, or whatever, yeah. Whatever, plus the minus the projection. Inclusion to G and projection to H. If I put there this minus, then everything is perfect. Those two things avoid each other. I just take the same minus the diagonal. We take now that thingy and minus the diagonal of the same matrix. If you look at when can a thing of this form be equal to a thing of that form? Only when it's 0. That's it. We won the case. And in particular, when, say, for G is equal to SL2, that's the previous example. And so what did we learn? That those B plus and B minus, therefore, are Lie algebras, or that those Borel groups are naturally Poissonly groups. Okay, so this gives us that B plus is a Lie algebra. And so B plus is Poisson-Lie. And okay, let me try to finish the final example. So these groups are potentially not so exciting because, well, the solvable things. One might say prefer some semi-simple thing. So let's try to find a semi-simple Lie algebra which becomes a Lie algebra. So let's take again G semi-simple. We can make it also compact, but for the moment I'll just take it split. For the double, we would take G plus G bar. I remind you that this means that here we take killing, and here we take minus killing. Do we have some nice, well, it depends if you saw this kind of stuff, then you recognize immediately that we have some nice Lagrangian Lie subalgebra. If not, it might be a weird question. But there is one very nice Lie subalgebra here, which is Lagrangian. You're worried about something.
What does the word split mean in this context?
That all roots are real.
Oh.
That everything is real somehow. Basically, that it's SLN. If it's of type A, then it's SLN R, and then for all other types, there is some particularly the most non-compact version of things. Or real version of the thing, when everything becomes real. Because I wanted to have, the reason for it, I wanted to have those Borels to be real. That's the reason. If I want them to be real, then better all those root things should be real. Okay, so this guy contains one nice subalgebra, which reveals the reason for this minus sign. What is it? It's the diagonal. G, I'll write it diag just to say what the embedding is. It is whatever. It is half-dimensional. It is a Lie subalgebra. And it's Lagrangian because there is this minus thing here. That's the reason for putting that is minus thing. But we need to find a complement for that. So need a Lagrangian complement. What kind of complement can we cook up? What the reason for making it split is that we're going to use this B plus B minus thingy again. Sorry. So let's start with, say, B plus direct sum with B minus part of, I should finish, but I'll do it in a minute. In G plus G bar, that's for the moment too big. That's neither Lagrangian nor complement, but it's already reasonably close to. So the idea is to take still a Lie subalgebra of those. And which one should we take? Let's think about it. You see, here we have this projection. Okay, now there is this projection going to H. Going to H plus H, and we should remove somehow one H from that thing. And so what we do, probably the best thing is to take the diagonal H and take the part which is somehow over the diagonal. Which, in other words, what it means for the case of SLN, it means that we take upper triangular matrix, a lower triangular matrix with the same diagonal. That's somehow what this requirement is. Just take a pair of matrices, upper triangular, lower triangular, with the same diagonal, except it wouldn't work. Now I see, so I will not take diagonal, but anti-diagonal. Anti-diagonal, so with the opposite. So let's take with the opposite diagonal. Why do I take it with the opposite diagonal? Because I want to have zero intersection with this G. See? That's certainly a nice Lagrangian Lie subalgebra that works very well. But I want to have intersection, so this guy is going to be called G star. Now, if I take this opposite diagonal, what we're going to have is the G intersection with G star is equal to 0. And so we won. We found this makes G to a Lie by algebra. And this is some sort of standard way how to persuade a semi-simple Lie algebra to be a Lie by algebra, or how to persuade a simple Lie group to be a Poisson Lie group. For the moment, it's for the split case. I'll describe it, say, for the compact case, either in exercises or next time. It's just some different version of the same stuff. And I guess you saw some quantum groups, at least SL2 or something like that, in the quantum topology class, and that's. I'm not sure whether we saw it for other semi-simple Lie algebras. Maybe just for SL2. That doesn't really matter. So that kind of thing can be generalized to arbitrary semi-simple Lie algebras. And it's a quantization, though I didn't explain yet what quantization is, of these things. So G is Poisson Lie. And when you quantize that thing to a Hopf algebra, you will get one of those quantum groups. Okay, so that's all for today.